Okay, so today I will talk about inflation and primordial perturbations, giving just a brief overview of the history behind why inflation was hypothesized and how we can use measurements on the CMB to constrain inflationary models. So to start with, we will discuss this cosmic microwave background. So the extremely uniform radiation that was emitted during the early universe as it cooled down from an opaque hot plasma. Now, if we look at the CMB image taken from the Planck satellite, we see that there are these deviations, these temperature deviations, even though it's extremely uniform. If we look here, so if T0 is the mean temperature, then the deviations with respect to the mean are roughly of 10 to the minus 5, so incredibly small, but they hint of evidence that there were density perturbations in the early universe. Now, so before we look at inflation, let's look at the standard cosmological model pre-inflation. Now we assume that the universe is homogeneous and isotropic. So this is what's called the Friedmann-Lemaitre-Robertson-Walker universe. That it is extremely flat. So this parameter omega, which gives you the parameter which measures flatness, is very near zero. And that it's comprised of mostly dark energy, dark matter, and baryonic matter, and a very small amount of radiation at the current time. But over the course of the universe, this pie chart has changed as different energy densities dominate. And the solution given by the Friedmann-Lemaitre-Robertson-Walker universe is an expanding one. Its expansion is described by the scale factor A of t. So A of t gives you how the distance between the objects changes with time, and this depends on the main component dominating the universe, as we can see here, right? Where these W's are the equations of state for that given component, and for dark energy, for example, we have kind of exponential expansion. All right, now, so the problems with this model. There's multiple problems, but the main ones are the horizon and the flatness problem. In the horizon problem, we've seen that the CMB is very isotropic. And since the universe was initially radiation and matter dominated, this presents a bit of a problem because if we look at what is called the co-moving Hubble horizon, this quantity here, it tells us the distance at which two events are no longer causally connected because the expansion is faster than the speed of light. And we see that for radiation and matter domination, this grows with time, which indicates that two points quite far apart could not have been causally connected. So the question is, how can they have come to the same temperature? The universe, as we said, is very flat. And again, this presents a problem because it should diverge away from flatness, as this formula here shows. So how can we solve this? Well, we postulate a period of exponential expansion with an accelerating scale factor, and this can solve the horizon problem since co-moving Hubble horizon is now decreasing, so causally disconnected regions now could have been causally connected in the past, so they could have come into a thermal equilibrium. We also have the flatness problem, as we saw from the last formula, that for a sufficient period of inflation, the critical density converges to 1, so we have so the universe is kind of flattened during this expansion. Now, there are many different models which describe cosmic inflation, probably thousands, and the simplest is just postulating a homogeneous scalar field, which we call phi. Then the conditions necessary for inflation are a condition on the equation of state, that the equation of state is less than minus 1/3. So dark energy satisfies this, but since dark energy dominated quite late in the universe, it doesn't play into inflation. Now, this condition for the equation of state is related to what is called the slow roll approximation, which is that the potential of the scalar field must dominate over the kinetic energy, as you can see in this graph here, where the gray regions indicate periods of inflation. Right now, if we introduce the scalar field phi, there can be quantum fluctuations in the scalar field, and these will see density perturbations in the early universe, and these are what create those cosmic microwave background anisotropies. So the model of inflation also explains where these anisotropies come from. Now, by studying the CMP, we're able to derive certain observables that we can use to constrain our inflationary models. For example, the scalar spectral index or the tensor to scalar ratio. And while these have not ruled out all inflationary models, they have ruled out some, and future measurements will constrain which models can cause inflation and which cannot. Now, so we've said that inflation solves many problems, and that it's described by many models, and that by studying the that these fields create quantum fluctuations that create observables, and we can use these observables to constrain inflationary models. And future measurements will help us to constrain the model space even further and hopefully tell us something about how inflation happened. Thank you for listening.